They orbit between us and our star, hidden within the sun's glare, often visible only at sunrise or sunset. Venus, the first and brightest star in the evening sky, and Mercury fleeting across the solar disk. They are half of our solar system's terrestrial planets, yet we know so little. As we begin to take a closer look at our companions, they are posing more questions than answers. This is Mercury, the innermost planet closest to our Sun. Mercury's days are longer than its years, and it has an elliptical orbit from 47 million kilometers at its closest point to 70 million kilometers. Difficult to observe from Earth due to the Sun's light, Mercury is an enigma of the solar system's evolution.
Well, Mercury is really a weird planet. Normal terrestrial planets, all the rest, have a relation between how big they are and how dense they are. Mercury is not following that rule. It's much more dense than what you would expect for its size. That is not normal, so something went wrong in the formation of Mercury that we don't know.
Only 2 probes have been sent to investigate the planet, and only one has achieved orbit. Mercury is difficult to get to because of its orbital speed and the gravitational influence of the Sun.
Mercury, for us, is a planet of extremes. So you have temperature like 400, 450 degrees on the surface during the day, and imagine that's like being in a pizza oven on Earth. So it's really hot there, and temperatures at about minus 175 during the night.
Mercury orbits the Sun every 88 days in an atypical elliptical orbit. At its nearest approach to Earth, it is 77 million kilometers away. The first close-up imagery of Mercury came from the US probe Mariner 10 in 1974. With insufficient fuel to slow the craft, it was not possible to put the probe into orbit. Instead, it orbited the Sun, passing by Mercury 3 times. The flybys provided 2 interesting observations. Firstly, Mercury has a magnetic field similar to Earth, which is unusual due to the very slow spin of the planet. Secondly, the surface of the planet showed extensive cratering and very little volcanic or crustal movement. 2 contradictory observations of why the planet has such a magnetic field. The second and most recent probe is Messenger. Launched in 2004, it made several planetary flybys of Earth, Venus and Mercury to slow down to the correct speeds. It took 6.5 years to reach Mercury and enter orbit in 2011.
Because of this short distance from our central star, the temperature of the planet is very, very high. And when you want to fly around Mercury with a satellite, you find yourself in a very special thermal situation where you get a lot of heat coming from the planet itself that behaves like a thermal mirror. And then from the side you get the heat from the sun. So you have 2 heating sources which may destroy a normal spacecraft. Another NASA mission, Messenger, is getting operational in a very loose Mercury orbit because, as I said, the thermal situation is such that you better stay away from the planet.
Its primary mission was completed within a year, mapping the entire globe with about 100,000 images. With fuel in reserve, the mission life of the probe was extended. After 10 years, Messenger continued to send back information and observations. Magnetic field data, the magnetosphere, the effects of solar wind plasma, and studies of the atmosphere of Mercury. It is so low in density it is constantly blown off the planet as an exosphere, revealing the likes of sodium, calcium, and magnesium in a trailing tail away from the Sun. Spectrographic imaging of the surface material has thrown up more questions about the high metallic density of the planet. The observations do not fit the standing theories of the planet's evolution, which will have to be completely overhauled. One other interesting detail: at the north and south polar regions, Messenger has detected the presence of water ice in the permanently shadowed interiors of craters, just like on our Moon. In 2014, the probe was tasked to fly much closer to the surface, as close as 50 kilometers. There it imaged the surface at much greater resolution, hunting for more detailed signs of the planet's geological history. Left unaided, the probe continued to descend and ultimately impact on the surface. There was, however, sufficient fuel in reserve for 3 trajectory alterations to increase altitude and give the probe a short time extension to continue its work into 2015. A third mission to Mercury is underway by the European Space Agency and the Japanese agency JAXA. Bepi Colombo is named after the Italian mathematician Giuseppe Bepi Colombo, who first developed the gravity assist maneuver for NASA with the Mariner 10 probe. It consists of 2 orbiters, the ESA Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter.
What scientists want to do is try to understand the nature of the planet itself. What material is on the surface. We would like to measure temperatures. We would like to see the interaction with the solar wind. Then Mercury has a magnetic field, which is like Earth, a dynamo field. We would like to understand that.
The Japanese MMO will focus on the magnetic field environment around the planet, while the ESA probe will focus on the planetary surface. Like the previous 2 probes, Bepi Colombo will use Earth and Venus to slow the probe's speed down to drop closer to Mercury's orbit. This trajectory will take approximately 7 years to accomplish, with solar electric motors to maintain deceleration. Then a conventional rocket engine will be used for orbital insertion. The orbital life of the probes in the harsh environment is expected to last 1 to 2 years. The 2 craft carry a suite of the most advanced instruments, including a laser altimeter and magnetometer, infrared and ultraviolet spectrometers, imaging X-ray and high-resolution stereo cameras. Bepi Colombo is designed to answer specific questions about this planet. Why is the planet so dense? How did it form? Is the planet tectonically active? Why can no iron be identified on the surface? In the absence of any ionosphere, how does the magnetic field interact with the solar wind? How is the magnetic field generated?
We have a theory to understand how planetary systems form. Now, the theory was based on explaining the solar system, and it was fine, it worked. But now, when we have discovered new planets around other stars in the galaxy, the extrasolar planets, they don't fit at all. So something is wrong. And the special cases, those that are difficult to understand in the details, like Mercury, are very helpful.
By finding answers to some of these questions, Bepi Colombo will help us understand how the solar system was formed 4.5 billion years ago. It is the first and brightest star you see at night. Our sister planet in some ways, our closest planetary neighbor in both distance and diameter. However, Venus is difficult to reach and a very strange world when you get there.
In the early days of the solar system, Venus and the Earth must have been very similar. But then something happened and they took a different route in its evolution.
Venus is the only planet in the solar system that needs more time to rotate once around its own axis than it rotates around the Sun. There must have been a major disaster in the early history of the planet where it collided with a big other object. And this made it stop its rotation. The problem is that without the protection and without the rotation, the planet lost its water and so it's completely dry. And this, in the end, led to a horrible greenhouse effect that caused the temperature to rise to the levels that we see
One of the main differences between Venus and the Earth is simply that Venus doesn't have a magnetic field. So the way it interacts with the star is completely different. If you want to understand how did Venus get that way, why does Venus not have any ocean, you need to understand the interaction between the star and the planet.
The Soviet Union and the United States sent probes with some success. 3 Mariner spacecraft made brief flybys, and the Soviet Veneras entered the atmosphere and touched down, some surviving for minutes. They managed to send back tantalizing images of an almost serene vista. NASA sent 2 more probes, Pioneer Venus 1 and 2, the latter depositing 5 small probes onto the surface. The Soviets continued their program of Venera probes with 4 successful landers and orbiters. A further 2 Russian Vega missions deposited atmospheric probes as they swung by en route to Halley's Comet.
The atmosphere of Venus is incredibly interesting because it's so different from the Earth's atmosphere. And we'd like to understand what causes these differences, because this might well help our understanding of climate change on planet Earth.
There's a very dense atmosphere, to 97% of carbon dioxide, a very strong greenhouse effect, and the temperature down on the surface is more than 450 degrees Celsius. And the surface pressure is 92 bars, so it's almost 100 times more than the Earth. So it's a very, very unpleasant place to be.
High up in the clouds, about 100 kilometers from the surface, the wind speeds are very, very high. The wind is traveling at 300 kilometers an hour, and it travels around the Earth, around Venus every 4 to 5 days. So that's one of the things we don't understand, why at the surface the winds are very gentle, and high up the winds are very, very fast. So it's a very different atmosphere to the Earth's atmosphere.
0 and liftoff of Space Shuttle Atlantis.
In 1989, the NASA probe Magellan was launched from the payload bay of Atlantis en route to Venus, its 5-year mission to radar map the entire planet's surface. The radar managed to peer through the dense atmosphere and revealed the true face of Venus. What it showed was a young surface with few craters and mostly covered with volcanic activity, lava flows and large lava plains. Surprisingly, there was little evidence of wind erosion, and the surface plate tectonics were dominated by global rift zones, unlike Earth. To date, that was the last Venus probe from NASA. It was 12 more years before Venus came under scrutiny again, this time by ESA's Venus Express. To conserve fuel for a long mission, the probe utilized aerobraking in the Venusian atmosphere to make orbit.
Very interesting discoveries of Venus was a huge vortex, a huge cloud at one of the poles of Venus that in some ways looks very similar to a hurricane on the Earth. But this is a long-standing event that's there all the time. And we don't understand how it's formed, why it's there, and how it will evolve.
When we arrived at Venus 8 years ago, we detected winds at 300 kilometers per hour, very fast. But what has happened during these years, until now, they have actually increased. We now see winds of 400 kilometers per hour. And we can't really explain why that has happened.
More questions were raised by the planet's absent magnetic field.
Venus doesn't have a magnetic field. So Venus is just this big rock with this atmosphere and the ionosphere sitting in space, and the supersonic solar wind with the interplanetary magnetic field whacks into Venus, and it can't penetrate through the ionosphere. So the interplanetary field lines just sort of pile up ahead of Venus, like cars on a freeway. This solar wind whacking into it essentially sort of strips off the atmosphere, and it literally forms this long tail, like a comet, but stretching out into space. Pioneer Venus Orbiter was the first spacecraft to really thoroughly explore that night side region where the atmosphere is all escaping away, and it discovered this really mysterious phenomena which has yet to be explained. Imagine that we're flying from pole to pole on the night side, so we're feeling the plasma around us, and then suddenly the ionosphere disappears, and then it sort of comes back. And this is what an ionospheric hole is. It's like a chasm in the sky, a big hole where the ionosphere is just absent. So Pioneer Venus Orbiter basically measured inside these things, and we saw that there is very little plasma, and there's all this magnetic field. And from that, they sort of suggested that this is essentially a magnetic structure that's sitting in the night side. I wanted to see if I could go looking for these things with Venus Express. What we saw is essentially this really exciting, strong, straight magnetic field lines that we expected, and really boring plasma signatures. It shows us that this is a magnetic structure, right? This is a tube of interplanetary magnetic field that, well, PVO saw it coming out of the ground, and now we've seen it way out in the tail. So these things really continue out to much higher altitudes than we previously have found them at.
As Venus Express neared the end of its mission, scientists made some risky aerobraking maneuvers to bring the probe much lower in orbit to make close-up observations of the planet. These maneuvers involved daring plunges into the hostile atmosphere only 130 kilometers above the planet's surface.
For the aerobraking, we wanted the most area possible to get the most friction possible, but that also generates heat. And so what we did was we went into the atmosphere in this direction, because this face of the spacecraft, which had been attached to the rocket originally when it was launched, was most able to take the forces and the temperatures. We also turned the solar panels so that the side with the actual solar arrays was in the back to maximize the area as we went through the atmosphere, to maximize the amount of friction and to get the most amount of braking. What we saw that was a little unusual is the variability in the pressure, as if there were waves within the atmosphere. And so that possible wave-like structure was not expected, and we'll analyzing that data will keep scientists busy for a little while yet.
Venus Express carried a suite of 7 instruments: magnetometer, spectrometer, and several cameras to study the atmospheric winds and surrounding space environment. Venus Express outlived its planned 2-year mission by another 7, and only recently was it directed to ditch into the planet's atmosphere. The Japanese have made the most recent attempt to reach Venus with Akatsuki, whose planned observations are to include cloud and surface imaging with infrared cameras. Their main focus is the Venusian meteorology, including confirming the presence of lightning and any current volcanic activity. The probe failed to enter orbit on its first attempt, and JAXA are hopeful when the probe's heliocentric orbit returns it to Venus that a second attempt will succeed very soon. There are many plans afoot to return to Venus. Even a manned mission has been studied by various groups. One such study conducted for NASA produced HAVOC, a high-altitude Venus operational concept. It would rely upon 2 spacecraft sent into Venus orbit, the first unmanned atmospheric descent stage and the second orbital return craft carrying the crew. They would dock, transfer crew to the descent stage, and proceed to deorbit. Once into the upper atmosphere, a parachute would deploy, slowing the descent and allowing the deployment of a dirigible craft to inflate and carry the crew at high altitude. From there, they would study the planet below. The return journey for the crew would begin with a high-altitude launch back into orbit, where they would dock with the orbiter, transfer crew and equipment, and then make the journey back to Earth. There they could dock with an Orion capsule for the return to Earth. Mars, the god of war and the source of man's science-fictional demise. It has fired our imagination for thousands of years. We know the dry, barren planet was once flowing with vast reservoirs of water, the sky thick and filled with clouds, and the tantalizing possibility of life. It is the only other place in our solar system that man might one day call home. We Earthlings have fired numerous probes and satellites towards the Red Planet. An invasion of sorts, not for conquest, but for knowledge. What happened to Mars? Is there or has there ever been life on the planet?
A fundamental question that needs to be answered is life as we know it on Earth, even the simplest type of microbial life, unique? If we were to go to Mars and we were to find evidence of early microbial life, or maybe even present life that somehow survived in the near surface, would it be the same as the early life that developed on Earth? That's a very fundamental question. Does life emerge generally in planets where the conditions for life are favorable if we find out that they were favorable on Mars? Or might life take its own unique path in different environments and turn out differently?
We have bombarded Mars with satellites and landers, but there have been more failures than successes. The Soviets established 2 Mars orbiters, while NASA landed 2 Viking landers carrying complex analytical laboratories and searched for signs of microbial life. Their findings were inconclusive. Further missions to Mars still had a high mortality rate, but the successes were outstanding, with robotic probes operating for years beyond their initial missions. In fact, Mars is a planet occupied solely by robots on the surface and satellites peering down from above. All these instruments perform admirably in their specified fields of endeavor, giving us a much clearer picture of the planet and its history. The science was following the water, what happened to it, and where it is now.
Thanks to the specific instrumentation on board the mission, we are able to tell us what kind of ice did we find. And the result is that there is a mix of CO2 ice or carbon dioxide ice and water ice. And it's very important to characterize it, especially for the water ice or frozen water, because one of the main objectives of any mission to Mars is to trace the water on Mars in every form, liquid if possible, solid, water vapor. So it's very important to study the ice because it's one of the reservoirs of water on the planet.
The science was conclusive. There was water on Mars. There were ancient lakes and rivers, even an ocean. We needed to learn more. With the advancement of analytical technology, computer power and robotics, a new rover was constructed. Big, complex and heavy, it required a new way to land on Mars safely. Engineers came up with a system that couldn't be fully tested here on Earth. It required a lot of things to happen correctly, on time and in order. This was the Sky Crane, and the rover Curiosity was the first to try it out. A controlled re-entry with heat shield, aerobraking with a parachute, all pretty standard. Then a rocket-powered Sky Crane drops from the aeroshell and gently descends toward the surface, spooling out the rover below on cables. The rover touches down, cuts the cables, and releases the Sky Crane to fly off and crash harmlessly. The Curiosity rover has been an astounding success, traversing the terrain for over 10 years, taking samples, drilling and studying rock formations, zapping samples with a powerful laser, and photographing its progress.
Now, in the belly of that rover is an instrument called SAM. It's an instrument suite that has a couple different instruments in it that allow us to look at different types of gases. It helps us understand the chemical composition of the atmosphere and the end of minerals that might be found in the rocks and the soils on the surface. In particular, it helps us identify organic molecules that might be present.
So the sort of evidence we're looking for, sorts of signatures of past life that we would be looking for would be signatures of microbial life. So not realistically looking for dinosaur bones and that kind of thing. If life ever existed on Mars, we expect it to have been microbial, microorganisms.
Orbiters, including Mars Odyssey and Mars Express, have been hunting down life as well from orbit.
After 10 years of mission, we have achieved a global view of Mars, and then we know at every location on the surface if you find some special minerals or not. So we have really the global view that tells us the history of Mars. Mars Express has, for the first time, detected methane, and also the concentration in the atmosphere vary from a place to another, from a season to another. And this discovery has been very debated in the scientific community because, in fact, methane should not be there because it's being destroyed in the atmosphere by the ultraviolet radiation. So if methane is there, there must be a source of methane, and for the time being, the origin of this source is largely unknown.
However, with Curiosity prowling around Gale Crater, it too detected seasonal methane.
Now, methane has been found previously in the Martian atmosphere by both Earth-based telescopes and spaceborne orbiters. But this is the first time that we've actually seen a sharp increase and decrease in the abundance of methane in the atmosphere in Gale Crater. And what this really means is that present-day Mars is an active environment.
The big question is, what is the origin of this methane now being released? The two principal areas are, first, by analogy with the Earth, it could be released and produced initially primarily by biology. This would be microbial activity acting on certain chemicals below the surface and then producing methane as a byproduct. But of course we can't state with certitude that it is biologically produced. And so we also consider geochemical mechanisms in which carbon dioxide is actually combining with water and producing methane under very high temperatures and pressures. And that methane can then be released in the atmosphere separately.
Now, at this point, we don't have enough evidence to tell us whether or not the organics we're finding are biological or non-biological in origin. There are several viable non-biological explanations, including this organic material could have come down from space, from meteorites or comets, or organics can be formed by geological reactions in the rock itself. Now, what's exciting about this discovery is it gives us new hope in the search for chemical evidence of life. We found the organic material. Now, the next step is trying to figure out what its origin is.
Main engine start, ignition, and liftoff of the Atlas V with Maven, looking for clues about the evolution of Mars through its atmosphere.
The latest NASA orbiter mission is Maven. Launched in November 2013, it made orbit 10 months later.
Maven is the Mars Atmosphere and Volatile Evolution mission. Our goal is to study the role that loss to space has played in the history of the atmosphere. Where did the water go? Where did the CO2 go from the early planet? These are important questions to understand how Mars went from an early warm, wet environment to the cold, dry environment we see today.
There's evidence of water flowing on Mars at one point in time, perhaps even oceans on Mars. And what happened that it's so barren at this point in time? And a key part of that is the atmosphere, and it's a much thinner atmosphere than what scientists believe it was at one point in time. So the stripping away of that upper atmosphere, that's what Maven is going after, the climate change at Mars.
One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. The sun constantly emits high-energy photons. When these enter a planet's atmosphere, it can crash into a molecule, knocking loose an electron and turning it into an ion. When this happens in the presence of a magnetic field, the ions are captured and spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, these ions are carried away. Depending on where they form, other ions will not be carried away but will hit the top of the atmosphere. These ions crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. As this process continues over billions of years, Mars' atmosphere has disappeared, and along with it, the water. How much water has Mars lost this way?
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
Water naturally carries a heavy isotope of hydrogen, deuterium, which remains trapped in the water cycle while normal hydrogen is lost to space. Detecting the amount of deuterium enrichment tells us how much water has been lost.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
So in the ancient past, we have some indications of water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our oceans, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer.
It's fascinating that we can learn so much about 4.5 billion years ago what measurements are taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
Building on this knowledge, scientists are developing the next series of robotic probes to be sent to Mars in the coming years. This time, NASA is building on its successes, utilizing hardware and systems that they know will work.
We've been to Mars before with the JPL Lockheed Martin team. We've been to the surface of Mars before successfully with Phoenix. We know how to operate the arm. The surface operations are much, much simpler than Phoenix. And we're putting 2 instruments on the surface, and then we're leaving them there with no ground-in-the-loop interaction, repetitive, weekly uplink, downlink sessions. We're just made to do this mission.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
It's going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed. And what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be and composition.
The European Space Agency is also well along with ExoMars, a rover with advanced drilling capability due to be launched by 2018. Its principal goal? To drill down deep in search of microorganisms.
What is new with ExoMars, with the rover in particular,
is what we call the mobility. Mobility not only horizontal, but also vertical. And this is a peculiar thing that we have on board the ExoMars mission. So we will be able to sample material from below the surface. That is quite important to understand if there is any sign of past life activity on Mars.
We will be looking for the first time in the third dimension, the third dimension being depth. And we think that is where we have the highest chance of making an interesting discovery regarding the presence of organic molecules in Mars.
It's a whole planet out there with a complicated history. That history is a story that's stored in the rocks, and our job is to figure out that story and what that story of that planet tells us about this planet that we live on.
So where Curiosity takes rocks and grinds them up into powder and looks at their bulk constituents, what this mission would need to do is be able to look in a microscopic level and examine the rocks for these very tiny and detailed messages that they would be sending to us about the past life that could have lived there.
This that I'm holding up here is a classic biosignature from the Earth. It's a fossil. We're not actually expecting to see a fossil of shells or other components, but what we want to be able to see are, with this instrumentation, are the fine scale layering that one might see in a rock, in which we can see dark and light toned layers. And those dark and light toned layers are telling a story.
When will NASA send astronauts to Mars?
4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
The first test flight of the Orion crew capsule is complete. The hardware and systems are ready for mass production. The components, the engineering, the manufacturing are all underway, with NASA looking back to what worked in the past and utilizing it for the future. The solid rocket booster technology straight from the space shuttle has been extended and tested. NASA's new Space Launch System, or SLS, is coming closer to fruition, reusing the space shuttle's main engines as the new system's workhorses, saving billions of dollars and years in research and development. The Europeans are teaming up with NASA to provide the service model for Orion, allowing for long-duration, deep space flights. Autonomous Martian landing systems are well advanced and being tested. Software and hardware are fully integrated for both manned and unmanned Martian landings. And when they get there,
Desert RAT stands for Desert Research and Technology Studies. This is a group of engineers and scientists.
We're looking to test out new concepts, procedures, equipment, like rover concepts, to see how they work in the field environment.
So the team tests these technologies to make sure that in future human spaceflight missions we'll be able to do science as best as we can. That's something that NASA's never done, two human rovers at the same time. So we're really trying to develop how do you use these assets at the same time, and interesting things that you might not think about are your communications. So you potentially have 4 astronauts talking all at the same time to mission control or science communication background.
It's just like running a real mission, say, like you can think about the Apollo mission to the moon. You had the astronauts to the moon and you had the people in mission control, but there was a science backroom you didn't hear about, but the astronauts were getting information from them.
Arizona has a very good climate for these types of analog studies. You have pretty much open plains and you have a lot of geological features that are analogous to places on the moon and on Mars.
Long-term space voyages are being replicated on the ground and in orbit with the ISS. Surface habitats, power systems, food and oxygen supply manufacturing are also on the drawing board.
The human flight component would like to see an experiment where resources on the surface of Mars from the rocks or the atmosphere could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
NASA isn't the only one with its eye on this prize. ESA and now the Indian Space Research Organization have a spacecraft orbiting Mars, and they did it on their first attempt. Private enterprise is hard at work as well. Mars 500, Mars One, the Mars Society, Mars Foundation, and the Mars Initiative, to name a few. And they have volunteers lining up already for a one-way trip to Mars. It is inevitable that we will set foot on Mars in the very near future. We will stay and learn her secrets. Perhaps in the future we will be able to alter the atmospheric density through terraforming and return Mars to the world that it once was, awash with oceans and rivers, clouds and rain. Maybe some of us could call it home. From the beginnings of our solar system 4.5 billion years ago, there remain tantalizing clues to its evolution. Remnant debris, asteroids and comets. They vary in size from grains of dust to mountainsides, from footballs to planetoids. They were the building blocks of the planets and perhaps carry the origins of life itself. Now within our grasp, these rocks of ice and dust are ready to give up their secrets. Asteroids are believed to be made of chondrules, flash-heated grains of rock within the stellar disk of our forming solar system. These chondrules clustered together, forming the first asteroids and the building blocks of the planets. Once the solar system had evolved, there was a lot of asteroid material left over. They cover a broad spectrum of types. The largest of these are minor planets or planetoids, large enough to have an ovoid shape. This category took the previous planet Pluto off the major list and onto the minor. The smallest remnants of debris are often called meteoroids. There are in fact several minor planets. Some have been seconded into planetary orbit and become moons. The traditional asteroid belt between Mars and Jupiter has one called Ceres, the largest and the first to be detected. Our first close-up of an asteroid was courtesy of Galileo on its flight through the main asteroid belt towards Jupiter. It photographed 951 Gaspra, an S-type asteroid with an average diameter of just over 6 kilometers. The S stands for stony composition. Galileo then photographed the larger 243 Ida at 15.5 kilometers wide, revealing that it has its own moon named Dactyl. Asteroids are not limited to the asteroid belt between the orbits of Mars and Jupiter. Many orbit much closer to Earth and are known as near-Earth objects, or NEOs.
Radar is a very powerful instrument that we use to study near-Earth asteroids. Asteroid Toutatis was millions of kilometers away, and we were able to resolve surface rocks. We could see boulders.
There are currently only 2 radar facilities in the world that have sufficient sensitivity for doing regular observations of near-Earth objects. Arecibo, and Goldstone.
Even the most powerful optical telescopes, and I'm talking even, Hubble telescope, they can only see this asteroid as a point of light. It is just too far and too small.
It provides an extraordinary opportunity to get very detailed radar images.
You are transmitting microwaves. It's propagating at the speed of light toward the asteroid. It is bouncing back. And this radar echo is containing surface features of the asteroid. It's telling us about its rotation, and it's very precisely pinpointing its distance from the radar.
These asteroids were imaged with ground-based radar. BL-86 revealed it has its own moon, and asteroid HQ-124 passed very close to Earth, some 3¼ times the distance to the moon. It is due to return sometime in the 24th century. Scientists are looking much more closely at these objects for their potential to pass through Earth's orbital plane and perhaps pose a threat. The most common type of asteroid is the C-type carbonaceous, accounting for about 75% of known asteroids. The probe near Shoemaker was the first dedicated asteroid probe launched by NASA. It photographed 253 Mathilde, a C-type, then moved on to 433 Eros, the largest visited at the time, where it orbited, took extensive measurements, and, more by accident than good planning, landed on the asteroid, the first probe to do so. Deep Space One, an experimental NASA probe, was sent to investigate an asteroid 9969 Braille. Technical errors returned poor imagery. However, the probe continued on to its second rendezvous, for the first time with a comet, 19P Borrelli. Comets are closely related to asteroids, but originate from the cold, dark outer boundaries of our solar system.
Comets are bodies in our solar system that have been left over ever since the solar system formed, some 4.5 billion years ago. And therefore, when we look into comets, we look into the past of our solar system. And so by investigating the details of comets, how they formed, how they evolved, we can actually have a glimpse into how our solar system formed, and in the end, how the Earth formed and why we are here.
Comets have been recorded throughout history, as they are easily observed when close to the Sun, often considered an omen. One comet of note was Halley's. In 1986, Halley's comet returned once again, and this time it was met with a veritable armada of space probes. The first attempt at a space rendezvous was with the International Comet Explorer, or ICE. It passed through the tail of comet 21P Giacobini-Zinner on its way to meet Halley. The European Space Agency sent Giotto. The Russian and French sent two probes via Venus, Vega 1 and Vega 2. Japan sent Suisei and Sakikage, that country's first deep space probes. Their measurements went on to refine the targeting for Giotto to make a much closer pass of the comet's nucleus than first planned. In 1994, astronomers and scientists were given an unexpected treat. Comet Shoemaker-Levy broke apart and struck Jupiter in a spectacularly violent fashion. Comets required more study. The Stardust probe was dispatched to investigate 5535 Anne Frank, Wild 2, and then the Tempel 1 comet. It returned a sample of cometary tail to Earth.
Our biggest discovery that we did was looking at this cometary material that was returned from NASA's Stardust mission. And the Stardust mission went up, rendezvoused with a comet, brought back very small amounts of material, comet material and comet exposed material. We had basically one shot at looking at this, and it was really pushing our limits of detection. So I spent about 2 years optimizing our technique, really rehearsing, practicing, getting everything as as perfect as possible before the one day of doing measurements. It's sort of all leading up to one big game, one big day. And also just working with meteorites and working with the cometary material, I'm working with something that's 4.5 billion years old that very few people ever get to play with, and the few days of being able to do the actual measurements make up for all of the rehearsals that it takes.
JAXA launched Hayabusa to study asteroid 25143 Itokawa and to retrieve a sample from the surface in a touch-and-go maneuver. The mission took a total of 7 years to accomplish, with the sample return pod retrieved from the Australian outback in 2010. Launched a year earlier by the European Space Agency was a very ambitious spacecraft called Rosetta. Its goal? To land a probe on a comet, 67P Churyumov-Gerasimenko. Just getting there was to prove a challenge in astronavigation.
But when you want to rendezvous with a comet, you have to accelerate the spacecraft and match the same velocity that the comet has around the Sun. So this is the problem, not only the distance, but also the velocity. There is no rocket that can give us the velocity needed to be as fast as the comet. Like close to a planet, and you use the gravitational attraction of the planet to actually accelerate your spacecraft.
It passed by asteroids 2867 Steins and 21 Lutetia.
Lutetia is a very strange target, a very strange asteroid. We believe that it may be a C-class asteroid, which means that it is very primitive. However, it shows from ground-based and also spaceborne observations that Lutetia does not look completely like a C-type asteroid, and we are really puzzled about what it really may be.
The spacecraft then moved on to its primary target, Comet 67P.
The nucleus is pulling the spacecraft out of its planned orbit, and that can be seen as a shift in frequency of the transmitted radio signal from the spacecraft. And the extent of this frequency shift is a measure of the mass of the comet nucleus, so we are able to weigh the nucleus here.
There is no ice at the top, so it's covered by a mantle that we consider is essentially made of organic material. That's why it's very dark. And this material is one of the key things we would like to explore and analyze.
These organics may hold the secret to life on Earth.
What it's all about is the carbon chemistry. How much did the comets bring to Earth? So was it just the right elements, the right building blocks, or was there more information in it when these comets already arrived?
To try and answer these questions, ESA attempted one of the most daring missions mankind has ever undertaken, to land a probe on the surface of the comet. Landing on a comet is one of the hardest things that has ever been done by the human species.
This is the comet. It's roughly a 1 in 1,000 model, so the real thing is 1,000 times bigger. The landing site is roughly here, which we're aiming for to deliver the lander. It's the flattest part we could find. What we are studying at the comet with the instruments are basically what are the ingredients, which materials are present, and coming back to one of the objectives of the mission, how complex are the materials present at the comet.
Landing means flying very, very slowly over the comet and then gently pushing away the lander. It's not a landing like you can imagine on the moon, where you come with rockets and you have to brake. Here the problem is the opposite. You have to really touch gently the comet. The forces involved are very small.
If I get meaningful data, that would be just marvelous. If the descent works, the landing is okay, we receive a sample, and the whole thing runs smoothly, that would be just great. But we need a lot of luck, really. And we had a lot of luck already.
So we are sitting on the surface. Philae is talking to us, more data to come and to be analyzed right now. Going down, which it should do, of course. We are there, it's done its job. We are on the comet.
The science has started now. We have the first results that give us the first comprehension of what we think the comet is, where it started from. Now, for the rest of the year, we'll watch how the comet evolves. We'll unlock how the comet works. We're looking at where the gas and the dust start to accelerate from the surface and how that beginning of the coma, that birth of the coma works. So how the coma develops as it does to higher altitudes. This region has only ever been theoretically constrained or modelled. These will be the first measurements we make in this area or this region, and that's a really big, important target for us.
Eventually, the tiny probe shut down.
Having Philae reactivated is not so likely, but it's not impossible. Philae was designed to hibernate, was designed to switch off and be able to reactivate itself. Of course, we expected this to be a duration of a few days or a few weeks, not a few months. But okay, we will see. Maybe we are lucky and the units have survived these months and will reactivate in June, July.
While observing the asteroids, scientists were surprised to find one with what looked like a cometary tail. After careful study, scientists realized they were observing the results of the impact of two asteroids. 596 Sheila had been struck at high speed by a small asteroid. The impact hit with the force of a 100-kiloton nuclear bomb. NASA had done something similar with Deep Impact, a probe sent to Comet Tempel 1, where it dispatched a kinetic impactor which struck the comet to study the impact and the debris thrown up as a consequence. Soon after, NASA launched another small ion-powered probe, Dawn, which also had an extraordinary mission: to travel deep into the asteroid belt between Mars and Jupiter. Its targets, two of the largest asteroids in the solar system. Dawn rendezvoused with 4 Vesta and orbited it for over a year, returning a wealth of data. Dawn then departed and cruised towards Ceres, the largest of the asteroids, a planetoid, where it has obtained orbit and begun its study. JAXA, the Japanese space agency, has recently launched a second Hayabusa probe, this one with many improvements over the first. Its target is the C-type asteroid 1999 JU3. It's expected to reach its destination in 3 years, collect samples, and return to Earth by 2020. NASA has announced the OSIRIS-REx sample return mission to asteroid 1999 RQ-36, better known as Bennu. It's expected to launch sometime in the near future, and after a 2-year journey, orbit and map the surface before touching down to retrieve 2 kilograms of material. The probe sample's return is expected in 2023. There is also a practical reason to study asteroids. In 2013, an asteroid with a mass of about 9,100 tons exploded over Chelyabinsk, Russia, with the force of 20 Hiroshima bombs, causing 1,500 injuries and damaging 7,000 buildings. It isn't the first asteroid strike on Earth, as the dinosaurs can attest to, and probably not the last. Through the United Nations, ESA and other major space agencies have established a safeguard program.
The NEOWISE data have returned 2 very important findings. First, we've been able to determine that we've found 93% of all the near-Earth asteroids that are out there that are larger than 1 kilometer. We've also been able to tell that there are somewhat fewer near-Earth asteroids that are larger than 100 meters than were previously thought. However, fewer does not mean none. That leaves about 15,000 asteroids larger than 100 meters that remain to be found.
This advisory group is also planning intervention missions if needed.
We think that we can cope with deflecting an asteroid with 2 different technologies mainly. One is what we call kinetic impactor, hitting the asteroid and pushing it out of the way. The second one is take a heavy spacecraft and use it as, say, a gravity tractor. So by the mass of the spacecraft, you pull the asteroid away.
There is one project in the planning stage to snag a small asteroid in the near-Earth region and drag it into a lunar orbit. There it can be met by astronauts aboard an Orion capsule who will study the asteroid firsthand, take extensive samples, and return to Earth. the more we know, the better prepared we are to protect our place in the solar system.